Can you guys see my screen? Can you see anything?
I can, at least.
You can or you can't?
Yeah, I can.
Okay, awesome. Okay, so we can get started right now. I'll start with the basic set inclusion proof. So here it says to show that A minus B minus C is equal to A minus B minus B minus C. So I'm going to start with the right-hand side first. So A minus C minus B minus C is, it tells me that X is in A minus C and X is not in B minus C by the definition of the negative sign, which is complement, basically. So X in A minus C tells me that X is in A and X is not in C. X in not in B minus C tells me that X is not in B because B minus C is a subset of B. I hope that makes sense. Okay, so we need to show that we get this. So we have X in A from here and X not in B from here. Sorry. X not in B, which is X in A minus B. And from here, we know that X is not in C. So X is in A minus B and X is not in C. So X is in A minus B. Sorry. Which is what we have here. So we proved that our right-hand side is equal to the left-hand side. Okay, and the second one was about Venn diagrams. Let me pull up the question. Sorry.
Oh, I was just gonna
Yes?
ask if anyone else had that problem. Yeah, because for other people it looks fine.
No problem?
Just someone said it your screen was sideways.
Oh.
No, I don't know. To me it looks fine, but
Okay,
and someone did ask if we're allowed to use set identities, because I was gonna ask if that's how they learned it, because I remember when I did the course, we definitely did it a different way.
Set identities are like, okay, maybe, oh, yeah, because I remember doing it this way and I got full marks. But yeah, I'm pretty sure set identities also like works. So A minus B is also the same thing as A intersection B complement or section B complement.
Yeah. That tilde there is complement. I think also you can do the line on top if anyone's confused.
Yeah, it's the same thing, basically. I remember these proofs don't have to be that formal from at least when I took the course. You could like write it out and it would be fine too. Is that okay? The second question. Okay, I'll move on if no one has any questions. The second question was about like Venn diagrams, and let me pull up the question. Okay, so it was A intersect B minus C. So B minus C tells me that it's B intersect with C complements. Everything is in B that is not in C. And then the intersection of A with that. So everything in B that is not in C is, sorry, it's this part, and then it's this part. Wait, hang on. Everything in B intersecting with, everything in B intersecting with everything not in C. So everything not in C is this portion and then this. Yeah, so it's that. And then and A intersect with that portion is also just this. So we only shade this part. Does that make sense? Okay, awesome. And then the second one was A intersect B union A intersect C. So A intersect B is this whole part. A intersects, I'll just shade them and like to make it easier to look. A intersect B is this. A intersect C is this. So the union of both those regions is just this. Like you don't have to take anything out. So that should be pretty straightforward and easy to like go about. Okay. And then there's A intersect B. Oh, this question is just repeated? That's just a repeating question. Okay. So these were the questions from the forum. I'm gonna move on to some of the questions from your exercises, which is from chapter 2. Let me pull that up. Okay, I'll start with C. Is A minus B minus C equivalent to A minus B minus C? I mean, we already have that above here, so you know it's false. But we can show an easy counterexample for this. So I know this is false because we have this identity above here. And I can let my counterexample be, okay, we'll let A equal to 1, 2, B equal to 1, and C also equal to 1. We'll compute B minus C first. B minus C is everything that is in B that is not in C. It's B intersect C complement. Sorry, everything that is in C everything that is not in C intersecting with everything in B. Sorry, that was a brain fart. Okay. So that would be, this is this is obviously going to be the empty set because it does not look right. That doesn't look right either. Whatever. And then A minus B minus C is just equal to 1, 2, because we're just taking away the empty set. But A minus B minus C would be, so we can compute A minus B first, which is, oh, sorry, I'm just checking chat right now. Do you know how many questions were in your midterm? We had like a lot of questions. I think we had like 12, around 12. It was a long paper. Or 20. Hold on, 20 questions, I think. Not even 12. It was a lot. I remember a paper being very lengthy. And I couldn't, like,
Yeah.
I barely finished in time.
I actually think my year had more than that too. Like none of them were super hard. They just threw so many
They're
questions
very
at us.
lengthy.
But like they weren't hard as long as you knew the practiced a lot. I think that's definitely the most important thing.
It was very similar to the assignments and the practice questions, like these questions. We also got them. They're very similar to it, I think, except for like a few curveballs, I think. But yeah, sorry, I'm gonna keep going. A minus B is just 2. And then C is equal to 1. So yeah, that's A minus B minus C is equal to A minus B intersect C. And that's just this. So we don't. So A minus B minus C is not equal to minus C. Okay. And then I'll go on to another subset inclusion proof. Okay, this is a good one. G tells me that A intersect B. Wait, sorry, any questions about the part before? Can you guys hear me?
Yeah, we can hear you.
Oh, okay. Sorry, I thought like I was just talking, no one was hearing. Yes, you do. It's always much easier to not how do you compare the quality? Like, you want explaining that? Not sure if I'm understanding it right. Oh, like that, like the set inclusion thing. Okay, yeah. Yeah, you can do that too. I just think making a counterexample is, like, much easier sometimes than doing the whole, um, the whole thing. Yeah, if you're under a time crunch, definitely do the counterexample stuff. But whatever you find easier, honestly, they're both, like, they both are gonna fetch you full marks. Okay. I will do this question. Intersect B. Also, if you guys have any other question that you want me to go over, you can, like, drop it in the chat. Because right now I'm just going off of whatever was mentioned in the Google Forms. So yeah. Okay. A intersect B union A intersect B complement is equal to A. We can use the distributivity laws here, which are in your, I think they're in the back of your, um, like your practice problems. Let me pull it up so I don't get it wrong. Okay. So using the distributivity law, this is the same thing as A intersect B. You can basically factor out the A intersect, and that gives you B union B complement. And you know that B union B complement is basically B and B or everything that is not B, which is the universe. That's like everything. So that's A intersect the universe. A intersect the universe is just A. So that's how we get that. Any questions?
Maybe like
I'm gonna
write
guess no.
down the laws beside them just in case, or like I would recommend that for anyone doing it on the midterm.
Sorry, right,
Because
what?
like the laws you actually
Oh,
use
right.
while doing it, because I can't guarantee someone would get full marks without rating them. Um, like they might not. I have no idea.
Is that, yeah, you're right. We did have to write the laws beside them.
But yeah, it's good practice anyways, because those laws are like used
Yeah.
for the rest of your university degree. Like they're just very common.
Yep. Could we do this question? Sure. I feel. Okay. Okay. X plus Y floor of X plus floor of Y minus floor of X plus Y is equal to 0 or 1. Hmm. This looks like it's true and it has to be a proof by cases. If we were to do, oh, sorry, question, A minus B equals A intersect, how would we say that we use it, if that makes sense? Yeah, you could say by definition. I think that's what I did in my year.
Are is
Wait,
there
yeah.
Sorry?
Wait, what are we doing right now? I kind of
We're
lost
doing like
track
the
of.
question. We're doing that question, like the proof question. Hakeem, do you want to
okay.
take over?
Yeah, I can take over this one.
Okay.
Yeah.
Awesome. Thank you.
Yeah, I'll do something after. Well, whenever.
Can't stop sharing my screen.
Okay, wait. Let me. Okay. Yeah, okay. So this question was who's up? No, it's down. That was the one of these guys. Okay. And then let me just snip this. Unfortunately, I don't have a tablet, so I can't really like, but I could still use Paint, I think. Yeah. Okay, so this collection, yeah, these problems are kind of tricky because it's tricky to like kind of work out because you can't really, there's not really any rules for like these kind of statements. My mic's open, right? Like you guys can hear me?
Yeah.
Yep.
Okay, nice. Okay. Yeah. So for this statement, so really for these types of questions, there's really 4 different cases, and by symmetry, you can actually argue that there's really 3 different cases. So there's the case where x is like let's say x is an integer, right? And where x and y are both integers, let's just say. And then there's also the case that x and y are both not integers. So they're both not integers. This kind of writes like that. And then there's the case where one of them's an integer and one of them's not. We'll just say that x is an integer in this case, right? And then y is not. Okay, so in this case, right, for this case, right, we get that the left-hand side, right, left-hand side is just simply just x plus y, right? And then minus x plus y, and then you can kind of distribute the negative, so this becomes 0. So this checks out, right? And then for this case, right, so we get the left-hand side is simply, what is this, x plus 1? And then the other one is y plus 1. Not plus 1, actually, it should be plus some remainder term. So we're just going to do on x. And then the other one is just plus y plus some remainder term, epsilon y. And then this becomes, yeah, you can do it in terms of inequality too. You can kind of bound it so that I can try that method as well. Essentially, you get x plus y, and you get plus epsilon x plus epsilon y, right? And then the x plus y's cancel, right? And the thing is that actually this becomes also this. Yeah, the problem with writing it. Oops. Okay, I don't know why the eraser does that, but the problem with this is that this is actually rounded up, right? So this could be either x plus y plus epsilon x plus epsilon y, right? Or the same thing like +1. Let's see, write a +1 term here. Right. So in total, this ends up being either 0 or 1, depending on whether epsilon plus x plus epsilon y is oh, interesting. Okay, you did it. You lost marks for not doing that way. Okay, we can try that way instead. Okay, so to do that way, inequality way. Okay, so I'm assuming when you mean inequalities, you mean that x is a real number, so therefore it's implies that it's in between some integer k and k plus 1, right? And then yep. And then y is a real number, so it's in between some integer m and m plus 1. Or I wrote x here, it should be a y right here. Okay, it should be a y, right? So that means that floor of x is simply k. Floor of y is simply just m. And then floor of x plus y is less than or equal to k plus. Well, in order to solve what this is, actually, you have to kind of bound what x plus y is. So you know that it's in between k plus m, right? It's less than or equal to k plus m. And then this also should not be less than or equal to sign. It should be strict equality right here. Yeah, strict inequality right there. Oh, you're right. This is ceiling. Okay. Yeah, no. So just replace these with +1. I completely thought this was, yeah, there we go. And then if I can move this right here. Yeah. So yeah, you want to bound it. So it kind of looks like that. Yeah, that's right. And then this should be strictly less than k plus m plus 2. Okay. And then so I'm trying to think, is this if it goes up to m plus something, suppose it could. Yeah, okay, this is good. Yes, this is good. And then what you want to do is, you know that it has to be at least k plus m. So if you write this floor right here, right, you know that it's at least k plus m, and it's either and you know that it's also has to be less than k plus m plus 1, so strictly less than k plus m plus 2. Okay, so now you've handled the cases. So case 1, x plus y is exactly equal to k plus m, or rather the ceiling, then means that x is equal to k and y is equal to m. So then you get that I'm just going to write this as the equality right here. So this is simply just k plus m plus 2, and then minus k plus m. Yeah, right. Yeah, minus k plus m. Okay, yeah, okay, so this is a good thing to watch out for. Okay. So it's only equal to k plus 1 if so I should instead write it like this. I should say so plus if x is strictly greater than k. This just means that it's equal to the k plus 1 if x is greater than k. You can write it down like I just wrote it down like here just to be like quick because I know that in order to answer any questions you guys have, but I'm just gonna write it like that. And then Okay, so now the case. So if this is exactly equal to k plus m, that means that x must be k, y must be m. So that means that this whole thing simply just becomes k plus m minus, and then in the, oops, and then inside should be k plus m, so it's 0, so the sum is 0. This is the case where this handles this case. Okay, next one is the other case is, you know that x plus y has to be equal to k plus m plus 1, right? Now in this case, there's really two sub cases. There's one of them is, you know, one of them is an integer, or both of them are not integers, right? Because you know that in the case where both of them are integers, this is what happens. So for the sake of, actually I should handle both cases, yeah. Okay, so if x is not an integer, right? And y is not an integer, right? Then that means that this whole thing becomes, so this this should be k plus 1, and this is the term that represents this, and then this should be m plus 1, so that's the term that represents this, and then this should be minus k plus m plus 1. So this is exactly equal to 1, right? And then in the other case where, like, let's say they're both integers, or sorry, no, they can't be both integers. One of them is an integer, and the other one's not, then s just becomes k plus 1 plus m, or sorry, k plus m plus 1. It's really the same thing. Minus k plus m plus 1, so it's equal to 0. And then also, if you wanted to be fancy, you could actually skip all this stuff. And then what you could do is you could say, okay, well, this plus this has to be more than or equal to, or sorry, has to be less than or equal to k plus m plus 2. And, oh, okay. Okay, yeah, I'll redo it from like a high level just because I think there's a lot of stuff here, but okay. You could say this, and then you could say x plus y plus, or sorry, this ceiling is more than or equal to k plus, yeah, yeah, yeah. So high level, basically, you want to split up the case for which, okay, so you should write down this, right? Let me highlight in red. You should write down this, right? Okay, so that will tell you, and then from that, you can get something that looks like this, right? And then you split on cases, right? Because you know that this quantity, x plus y, is an integer. So you know there's only really two possibilities here if it's bounded between two numbers, right? So it's either k plus m or k plus m plus 1. Now for the case where where it's k plus m, then that means that you know that both of these guys have to be integers. Otherwise, by the definition of ceiling, this should have been rounded up to k plus 1, or this should have been rounded up to m plus 1. Therefore, this case is easy. Now for the other case, one of them has to not be an integer. So you can do kind of two proofs based on what you could say here. Instead of actually doing two proofs, what you could say, you could combine these kind of sort of things and say that, okay, so x plus rounded y is less than or equal to k plus m plus 2 less than or equal to k plus m. And then you could just subtract both sides by this quantity, and you get that it's in between 0 and 1. Wow, we did these proofs in class. Yeah, that's yeah. Yeah, so you see how they handle the cases? They handle first the case where m is less than 0 and m is more than 0. Here it's similar, where we handle different cases. So we handle the case where, okay, the rounded version of x plus y is k plus m, and one where it's k plus m plus 1. And then you can go from there. And then if you wanted to combine these two cases, you could just simply just use this statement and then subtract both sides by this, which is the same thing as subtracting both sides by this. And you get that 0 is less than or equal to the quantity less than or equal to 1. And you get something that looks like that. And then that is exactly what the proof statement says. So is there any questions? Does anyone, is this a valid solution for the problem? Let me see. N equals that. Actually, I should copy and paste this so that you guys can see this as well. Oops. Let me zoom out here. Make some more space. Paste that in. Okay. Okay, so the question is this a valid solution? Okay, so x plus y, the absolute value of x plus r. Yeah, yeah, that works. Yeah, no, that works. And then equals. Okay, so this step to this step right here is a little questionable, and that's because that's because you don't know that the absolute value of r, like rounded up, is equal to 1. And same thing for s, like you don't know this, right? You really only know that this is bounded between 1 and 0. And s as 0 to 1. Yeah. So it could be 0, right? So like this 2 here, this could just be 0 instead of 2, or it could be 1, right? Yeah, that's the tricky part about these kind of step functions, is that you don't know whatever case it is. But it's still good that you use this R remainder and S term, because you could still use it. For example, if you wanted to continue this, you could probably write it as this. Minus R plus S. And then you just have to show that this is bounded by 0 and 1. And yeah, and then you could do cases on this as well. You could say, oh, if R is 0 and S is 0, that's one case. And then if one of them's not 0, so one of them's 1. Yeah. Yes. Yep. Is there any more? We can do another one, another floor function one, if you want. So let's take a look at the other one. Oh, I'm just gonna wait until I see a question. Okay, so the other one, what did the other one look like? Oh, okay, the multiplication and prove or disprove. Here's what I did for the floor type problem. Okay, I'm just gonna look at this first and then do the question. Do the next one. Oops. Oh my God. Oh, I think I just copied this whole thing. Undo, yeah. Okay, so let me see what this looks like. Copy image. Let me paste it here. Let me drag it. Okay. Okay, so I don't know if you guys can see that, but actually I should enhance it somehow. Okay, so, oh my God, that looks terrible. Wait, hold on. Is that better? Okay, so basically check both sides. Epsilon is, okay, x equals n plus epsilon, yeah. Consider the cases, epsilon's between 0 and 1/2. Yeah, Yeah, and then floor of that should be 0, so 2n. Yeah. And, yeah. Absolute value of x equals n plus, which is equal to n. Yeah. And then floor 2x, 2n, 2n plus 1. Yeah. Yeah. Yeah, this is a good proof. Yeah. Yeah. So yeah, usually with with floor function and ceiling, like you usually just want to expand on cases because it is a step function, so you kind of have to do cases. That's just how the function's defined. Okay, the other one is this one, right? Okay, so okay, let me try and make more space for this one. Okay, so this one was is this equal to absolute value or floor x times floor y? And it's floor, right? I didn't make a mistake, I think, right? Yeah. Oh no, it's ceiling. Oh my God. Okay. Yeah. So this should be replaced with ceiling. Then I'll just replace these with ceiling. I know that like I need to remove the bottom bars, but it doesn't matter. Like we could probably just ignore that, right? Just ignore this. So is the statement true? Well, whenever you see statements like this where you can take out something, usually means that it's not exactly. I mean, you can try cases, right? So like let's say x was some number n plus epsilon, and then y is n plus epsilon, or these should be so y equals n plus epsilon y, x equals n plus epsilon x. Okay, so now if we multiply these guys, right, if we multiply this out, then sort of what we're going to get here is n plus epsilon x and n m plus epsilon y. And that's the same thing as saying nm, right? So this part's fine. Nm, and then we got plus n epsilon x, and then plus m epsilon y, and then plus epsilon x epsilon y. Okay, so now you can start to see a problem here, which is that these terms here are kind of it's kind of hard to get rid of them. So you can kind of construct an example where, okay, let's say x is 1/2, and let's say y is, what is this, 2.5. Then if you multiply them, let's see what happens when you multiply them. Well, xy becomes something like okay, well, let's take the floor of this actually. So 5/2 times 1/2, so 5/4. So it's just get rounded to 2. Should be the floor of this, or ceiling of this. Should be 2. And then the other one is absolute value x and absolute value y, or ceiling. So this is 1 times 3. This is 3. So this is a counterexample which shows that it's false. Okay, now the key to picking this counterexample was to see this kind of middle term and trying to exploit it in some way. Now, imagine if m was 0, then this counter term would not exist. So you have to pick, I made sure to pick something such that m was not 0. And to do that, I just made it so that it's like y is greater than 1. So that makes it better. And yeah, that showed that's a counterexample to that problem. So that statement's false. Yeah. Usually for these proofs, we want to redefine it as like an integer plus a remainder, and then keep simplifying until we get cases. Yeah, that is a good way to do these kind of problems. Yeah. Okay. And then we could do another one. Let me see. Let me see if I can find another one. Okay. There's this one. This one seems pretty interesting. I could do, yeah, that one. Okay, so. Okay, so let me expand this. Make it a little bigger. Okay. And we gotta move this guy. Okay, so this one, you can kind of intuitively guess what kind of cases we'll be talking about, because there's multiples of 3 and there's like fractions. You basically have sorry, that was my Alexa. Okay, so basically, oh, okay, thank God. Okay, yeah, so basically, you want to write x as kind of x. So let's do what the comment said to do, which is write x equals n plus epsilon. Then that means that 3x just becomes 3n plus 3 epsilon. Okay, so now this whole thing sort of reduces down to 3 epsilon plus 3n, right? Equals, and then this should be floored as well, equals n plus floor of epsilon plus n plus floor of epsilon plus 1/3, and then plus n plus floor of epsilon plus 2/3. Okay, so you can get rid of the n's on either side. So it really ends up reducing to 3 epsilon equals this plus everything else. So plus the other thing, epsilon plus 1/3, plus the other thing, epsilon plus 2/3. Okay, okay, so let's consider cases. So let's say that epsilon was in between 0 and 1/3. Okay, so that means that this becomes 0. So actually, I should write it down as with red. So it becomes 0 equals, this is 0, plus this is 0, plus this is 0. So that checks out. Okay, now what happens if it's in between 1/3 and 2/3? Well, we're going to get something like, are you just subbing in 0? Oh, I just evaluated what each of these is. So this is, yeah, so I just evaluated it. So the basically floor of 3 epsilon in the case where, in this case right here, is going to be equal to floor of like some number r, which is, we know is less than 1. So 0, right? So I just subbed it in. Like this is exactly what this is right here. This one is exactly equal to this. This one's exactly equal to this. Does that make sense? Come out to 0, you conclude, come out. So since all the 3 terms you are adding would come out to 0, you can conclude epsilon is 0. 3 epsilon is 0. No. I mean, like, I'm so the whole proof statement reduces down to like proving this statement's true. This equality is true. So I just check both sides of the equality. So 3 epsilon, I know is going to be, like, I know that 3 epsilon is less than 1. And this only happens if epsilon is less than 1/3, right? So that's why the left side is 0. Check each of these guys as well. So I know that epsilon is less than 1/3, so therefore I know that this one is 0. And then, yeah. Can we just say that since epsilon is within that range, that it computes to like 0 without like formally showing it? Like, can I just say floor of 3 epsilon is going to be 0? Yeah. I don't think you need to compute that. Like that was just me explaining it. Like, yeah, I'm pretty sure that you don't have to say that. I mean, you never know. Like, you never know what the TA is going to do actually. So I shouldn't say definitely, but like. Okay, yeah. So for the other one, we get something like, what is this? This is still. Actually, this evaluates to 1, right? This guy evaluates to 1 on one side. Okay, so now this guy evaluates to 0. Second guy evaluates to still 0. And the other guy evaluates to 1. So this side actually works. And then the other one, now the other statement is that epsilon is more than or equal to 2/3, but it's still less than 1. And so let's see if this checks out. So we have, this is still, now this is importantly, what this implies is that 3 epsilon is in between 2. I should write 3 epsilon and between 3. So that means that the left-hand side becomes 2. This becomes 0 still. This side becomes 1. And this guy becomes, should be 1. So the statement ends up being holding true for all 3 cases. And since these are the only cases, then this statement is true. So yeah. So any questions there? Yeah, was there any questions for this question? Is there any comments? Yeah, usually for these type of questions, usually just need to, what is it? Oh, here's my proof for the previous ceiling question. Okay, let's see it. I probably need to do some rotations on this though. Okay. Okay. This is weird. Move it. Can I rotate it? I should be able to, right? Like it's a basic feature, right? Yeah. Rotate to the, oh, it should be, okay. Now at this point, it doesn't matter. Okay. Okay, so the proof went by writing x equals this, y equals this. Wait, what are you trying to prove here again? Was this for the, wait, which question was this for again? I completely forgot the question. Oh, this was for the first one that I did. Okay, yeah, this is for the first one I did. Okay. So for the case that is both between 1/2, yes. Oh, it's still less than. Oh, okay. Kimi, oh, okay, yeah, no problem. Okay, yeah, so these cases, shouldn't this be a less than or equal to sign, right? Unless you handled the case where they're integers already. But I don't see that here. Yeah, okay, so remember the case where you have to, yeah, for this one, you have to remember that x could be an integer. So in that case, epsilon of x would be 0, and same thing for epsilon of y. So therefore, the ceiling of x could just be x. So you have to be careful about that. That's case 2 and 3. Oh, I see here. Oh, you did, okay. Yeah, that works out too. Yeah. Yeah, you have to, oh, okay, I see. Wow, okay. Yeah, no, you already specified it. You know what? As long as you specified it, this should be fine. Usually people have it so that it's like a closed and then open bracket. that's fine too. Yeah, no, this is fine. This is fine. This is fine actually. Yeah. N plus n plus 2. Yeah. Or they're both. Yeah. Yeah. Yeah, no, this is fine. This is fine. Okay, sorry. I had to step out for a quick second. Yeah, no, this proof looks fine, I think. I didn't take a deeper look, but yeah, I think it looks good. All right. Okay, so we can do another set of 2 questions. Okay, so let's do. Okay, I'm probably gonna start a new paint thing anyway, unless I can expand this really fast. Yeah, okay, that's fine. Okay, so this question. So show that x cubed, or show that x squared plus 4x plus 23 is O of x cubed, but that x cubed is not. Okay. So there's really multiple ways to do this. So there's one way, which I'll denote with black. Oops. I'll denote with black, which is basically that you want to show that x squared plus 4x plus 23 is less than or equal to c of, or sorry, less than or equal to some number. Let's say, what is it like? We'll just say that it's less than x cubed for n greater than some number. We don't know what this number is, but we're just gonna say that. Yeah, so to show this, it's pretty straightforward, I would say, if you know your polynomials. So, I mean, intuitively, x cubed grows faster, right? But you can actually show this via inequalities if you just put everything on one side. So if you put everything on one side, you get something that kind of looks like this. And then if you can show, so if you could show the statement for some n, so for some n, then you're good. So if you could show this for some n, then you're good. So really, what you could do is, I mean, you could explicitly give an n, or you can say, oh, the limit as x approaches infinity for this quantity right here is equal to infinity. So therefore, that implies that there has to exist some n, right? So therefore, there exists an n. You could also say that this whole thing, x cubed minus x squared minus 4x minus 23 is always more than or equal to x cubed minus, and the rest of the stuff right here. And then you could show that this is necessarily like something like this, where like you use like an inductive argument, and then you show that this is, you can show that x squared plus 4x plus 3 is always less than or equal to, I think you would do like it's always less than or equal to, what is it, x squared plus 4 absolute value x plus 3, and then that is like less than or equal to 8 x cubed. So therefore, this whole thing is more than or equal to what is this? Since this is less than or equal to, then this whole thing's more than or equal to minus 8x cubed. And then if you put, probably if you put like a c, if you made this 8, or sorry, if you made this 9, then this would be a 9 right here, and then you could show that that is that remains unbounded. Okay, but that would probably not be good to write on test. So wait, did you guys cover the limit definition yet? I'm assuming you guys did, right? Okay, so if you did the limit definition, no? Okay, interesting. Like as in like, oh, if the limit of like over g of x, if that like goes to like 0, then that means that you know that f like grows slower. So it's a big O of g of x. Oh shoot. Okay, you guys didn't do that. Okay, interesting. Okay, so that means that you guys have to use another way to prove it. Okay, wait. Which method did you guys prove using it? Like, you could just say the method, and then I probably know what it is. Here's what my prof did. Okay, let's see. X squared, yeah. For x, yeah, yeah. Oh, okay. Yeah, no, that's pretty simple to follow. Yeah, so if you wanted to extend it to this, right? What you would do is just say, okay, well, I mean, you would do exactly what I was doing before, except like you'd probably do it more rigorously. So you would say, hey, x squared is less than or equal to x cubed for x greater than or equal to 1. And you'd say, oh, for x is also, yeah, each term is the highest power. Yeah, that also works too. That's basically what this is doing right here. So if you made it the highest power, then this would probably be like, this is c, and you'd probably have c be equal to like 23 plus 5, or plus 4 plus 1, to be more exact, which would be like 28, right? And then you'd just have, oh, 4x is less than or equal to 4x cubed, and then you'd have like, what is this? 23 is less than or equal to x cubed. And then this condition's for x more than or equal to 1, but this condition is for x more than 3, more than or equal to 3. So then you would write, oh, for x greater than or equal to 3, then x squared plus 4x plus 23 is less than or equal to 28 x cubed. Oh, this should be 23 actually. Actually, yeah, no, you could probably write it even more simply. You could just do x more than or equal to 1 here. Yeah, yeah, so 28x cubed. And then, yeah, I wrote it like, I mean, you could do like, to make it simpler, I just wrote it x more than or equal to 1 instead of more than or equal to 3. So, yep, x more than or equal to 1. So that means that for x more than or equal to 1, then that means that the whole polynomial is less than or equal to this. And so then you've chosen a c that's 28. So you know that that means that this is inside O of this. Yeah, and I think that's similar to what your prof did, right? Yeah. Yep, that makes sense. Okay, so is there any questions on and k? Oh yeah, and k equals 1, or n, whatever notation you end up using. So k or n, I don't know which one you guys did, but yeah. And then that satisfies the definition, therefore it's in it. Now, to prove that something's not in it is trickier because you have to prove that for all constants it's not true, right? So to prove for all n, so we have to prove that this x cubed guy is not. Okay, so ooh, okay. I gotta get a c and, yeah, you have to use a c and k value, but usually you can just use k equals 1, like in this case, and just follow the steps for polynomials at least, because polynomials are easier to work with. So I want to show that this 2x plus 1, oops, I should probably write it more neater. Oops, 2x plus 1. Okay, so this is equal to f of x, right? Okay, so big theta. Oh, I was looking at, okay, I was looking at this one. I forgot about this statement. Yeah, okay, so to do this statement, x cubed is not in the reverse. Okay, I'll save this for later. Okay, so to prove the counterexample, right? So to show that it's not in big O of x squared, you have to show that whatever c value you use will always go out of bounds, right? So, okay, so proof by contradiction works here, right? Assume that there exists some c, so and k. There exists a c and k such that for x greater than or equal to k, then x cubed is less than or equal to c times this whole thing, x squared plus 4x plus 23, right? Okay, then if you rearrange both sides, you're going to get x cubed minus cx squared minus 4cx minus 23c. And that always has to be less than or equal to 0. Okay, and okay, so for polynomials, right? Polynomials, you know that the highest degree determines like the evolution of the polynomial, right? And you know that the highest degree is positive, and it's just 1, right? So that means that you know that eventually x cubed will overpower whatever this is, right? So you can actually check exactly in terms of c, in fact. So what happens if we plug in x equals c? Okay, so if you plug in x equals c, then what you get is c cubed minus c cubed minus 4c squared minus 23c squared. Okay. So you know that this is obviously going to be, what is this? Oh, actually no, this shouldn't be a square. This should be 23c. Yeah. Okay, so you know that this is exactly equal to negative 4c squared minus 23, which is obviously less than 0, right? But you can see here that it kind of makes the equation simpler if we do this. So what happens if we write, like, let's say 2c, right? If we write 2c, we're going to get something that looks kind of like this. Okay, so 8c minus 4c, so we're going to get 4c cubed minus, and then 4 should be 8c squared. 8c squared minus 23c. Okay, and this is dependent on c, whether it's more than or less than 0, right? But the statement here is saying that it's always less than 0. So you can kind of see what's going on here, right? And if we were to extend it to the general case, then what you would have to get is that the thing is that you want to pick an x sort of that's like big enough where it can kind of swallow these guys whole. And picking one in terms of c is the best bet. Let me think exactly how you would do that. Or in fact, you could yeah, you have to show some kind of these problems are always tricky when you don't have the limit rules. Let's see. Okay, the way that sort of I would approach this, I don't know if this is what they taught you in class, right? So you would kind of write something like this, minus 4cx minus 23c. And then this is sort of less than or equal to, let me write it more explicitly. So it's less than or equal to, let me move this actually. Oops. Okay, so it's less than or equal to x cubed minus this whole, actually plus, you can kind of take out a c term here, x squared plus 4x plus 23. Okay. And then actually you kind of want to show that this is greater than actually. So actually this should be a greater sign. Should be a greater sign. Then this should be a minus sign right here. Minus sign. Then you know that this is more than or equal to x cubed minus c x. Okay, and then we want to find a bound on x squared plus 4x plus 3 in terms of, let's say, in terms of x cubed. So this is less than or equal to, this is less than or equal to x squared plus 4x plus 23, which is less than or equal to 8x cubed, right? Yes. But that would not, oh no, this shouldn't be an 8. This should be 28 actually. X cubed. Yeah. Oh, it should be x squared actually. Yeah, I'll make it x squared. 28x squared. Okay. And then this would become minus c times 28x squared. Okay. And then so you know that, oh, okay. And then the statement becomes obvious. So you know that for x, you want this to be, you want this statement here to be more than 0. Okay, so in order to choose that, what you kind of want to do is say, okay, well, in order to have that, we must have x cubed be more than c times 28 times x squared. And then to do that, we want to divide both sides. So x has to be more than 28c. Okay, so now that means that when x is more than 28c, this implies that this quantity right here, that implies that x cubed minus cx squared minus 4cx minus 23c, right? Yeah, is oh, actually, we should get rid of these absolute value signs. Actually, get rid of these guys. Yeah, and then this probably becomes something like this. Yep. Let me wrap this in brackets. Okay, wrap this in brackets, and then make these guys, this guy right here. There we go. Okay, yeah, okay. So this makes sense, and then, so that means that this quantity right here becomes more than 0, right? But we said here that it's always less than or equal to 0, right here. So this is a contradiction. That's a contradiction. Therefore, no C or K. Okay, so now to take it all one time, because I was trying to figure this out too. So you start with, okay, let me go back to the counterexample case. Yeah, okay, so you start with the statement. So the statement says that there exists C and K such that for all x with more than or equal to K, then x cubed is strictly less than this. Move everything to one side, right? Once you move everything to one side, you kind of want to prove that this is more than 0 for some x, right? So in order to do this, you want to kind of bound this this quadratic. And to bound the quadratic, you simply just get the highest terms. You just add them up, right? And then once you do that, you can kind of just plug that in right there. And then you can show that, oh, this doesn't work for x that is more than a certain amount. And then that gives you contradiction. So yeah, does anyone have any questions on that? I can zoom out just so that it looks better. I zoom out, I think. Oh yeah, sure. Let me expand this. Zoom out a little bit. Okay, so it should be this part right here. Yeah, there you go. So I can SS. Yeah, sure. It might not be helpful though, unless, I mean, I don't think I wrote it in a way that like it'd be easy to understand. Kind of looks like gibberish, but hopefully it works. Was there any more questions relating to this problem, or should we move on to something else, like complexity, like algorithm complexity, something like that? Or, oh, I think that there was another one actually. But I think the other one is easy, like this one. This one should be easy, f of x. Because I was told some STA said it should just be up to growth functions, I'm not sure. Okay, we can do both, it's fine. Yeah. So to do the other one was basically, it goes like, oh, f of x equals this. If I can move this, f of x equals this. And you want to show that this is in big O of x squared, right? You want to show that this is in big O of x squared. Okay, so to do this problem quickly, what you kind of want to do is, I mean, you want to do polynomial division here. So if you remember the long division rules, what is this? X cubed plus 7x squared plus 3. It's like equal to, this is 2x plus 1. This is like 1/2 plus, it's 1/2 x squared, I think. Oh, yeah, this is big theta. Yeah, so it's not big O. Sorry, if I may have said big O later. So yeah, this is 1/2 x squared plus, and then you could subtract kind of what this is. So minus x cubed minus 7/2 x squared. And the remainder here is 7/2 x squared plus 3. And then this sort of becomes sorry, completely blanking here. 7/4 should be 7/4 x, and then so this is minus 7/2 x squared, and minus 7/4 x, so it becomes negative 7/4 x plus 3, and you get minus, what is this, 7/8, and then so yeah, this is plus 7/8, and then plus 7/8. So then the remainder becomes 24 plus 7, which is 31/8, right? Yeah. And then basically, what's it called? Yeah, so f of x is exactly equal to 1/2 x squared plus 7/4. Sorry, plus 7 over 4, x minus 7 over 8. When plus the remainder, it's just like plus the remainder, 31 over 8 divided by whatever the thing at the bottom was, which was like 2x plus 1, I think. And then it's kind of easy to show that f of x is within big theta of x squared, because you can just notice that f of x is strictly less than or equal to the sum of these guys on the x squared term. So I'm just going to call it big C of x squared, where C is this sum right here. It's like 1/2 plus 7 over 4 plus plus 7 over 8 plus 31 over 8. And then you know that also f of x is more than or equal to half of x squared. Yeah. And the way to see this is that you just take one of the terms. Notice here there's a negative here, and that's tricky. But you can see here that for x bigger than 1, then this statement becomes true. Or for x bigger than some number, then the statement's always positive. Like this whole thing's always positive. So you can always remove it. And it's pretty easy to see that. So that's how you show that's within big theta of x squared. And then remember also your k values. Here it's always true, I think, for k more than or equal to 1. And then here you might have to do some like fiddling around with like this kind of thing, but it's a line, so it should not be too hard to see when it's positive. I think that happens for k more than or equal to 1/2. But yeah, so that solves that question. Is there any questions about this kind of way that I sped through showing that the rational function was in big O of x squared? Is there any questions about that? Okay. And okay, so is this a valid way to do the other question we just did, where we're saying x cubed does not equal there exists C? Yeah. Yeah. Yeah,
Oh.
honestly, this is I'm looking at the proof too. This is
That's how
fine.
I remember doing it as well. And
Oh, okay.
it
So
was
like you could
much
just use
easier to
limits
see
whenever
it
you
that
want.
well. Yeah. Well, not like whenever. It's because like in this case, like I don't know, you put it in a form where it's like much easier to see that it's because like in the original form, you can't really prove that
Yep.
the limit, like it's very hard to show that x cubed is less than whatever is on the right, but once you divide it by x squared, you can easily see that, you know, on the right side you just get c when x goes to infinity.
I mean, the thing is that you could divide both sides still, and that's essentially what you're doing here. And you could show that this goes to infinity. So therefore, that
Yeah.
means that, yeah, it can't be bounded by some constant c. So
Yeah, but the other way actually shows that like C doesn't exist. It's the same thing in the end, but I just remember it. Well, when I took it, them teaching us like that as well. The way that, yeah, the way that they put it there.
oh, okay, I see. Okay. Well, I mean, like, if you guys know that you can just use limits, then go for it. Just make sure that use the limit rules properly. And like, for instance, for the thing that they sent in chat, like if you can certainly divide both sides by x squared, just because, yeah, you can definitely divide both sides by x squared and then let x run to infinity. But also this exactly equivalent way, you can just divide both sides by like you can have all the terms on one side by dividing, and then you could show that this goes to infinity as well because the top side's a degree higher. So from calc, you know that it can't be bounded by some constant c, so that also shows it. Whatever shows it is fine. For the big data question, don't we gotta show both upper and lower bound by definition, and then say since the upper bound is x squared, lower bound is yeah. I think that's what I did. No, so okay, I can't even see the cursor. Yeah, so if you show that it's less than or equal to cx squared, and then I didn't even compute what c was, but I think you can just say c is equal to this. And then if you say f of x is also more than or equal to 1/2 x squared, those are two bounds that are both x squared, so it shows that, yeah. Okay.
And yeah, I think someone wanted the algorithm complexity.
Oh yeah. Yep. Okay, so which one? This one? B. Okay, yeah, B. Okay, so following algorithm gives us the multiplication of two n by n matrices. And then you want to find the time complexity and explain. Sure, yeah, you can show me what the prof did. Yeah, just paste in the chat. But basically, for this, if I were to look at this, right, just when you're analyzing time complexity, you want to sort of see what kind of operations take constant time and which ones are kind of what's it called, procedural instructions. So it's not procedural, like what is it called? Structural instructions. Like it's where instructions that tell you to like do a certain action multiple times. Okay, worst case, best case, average case. Okay, yep. Number of iterations of the inner loop. Yeah, okay, yeah. So yeah. The main thing is to be careful of what you're doing inside a loop and be careful what the bounds of the loop are. Okay, so when we first get into this, the non-loop instructions are this one. So setting constant to 0, and then also setting setting a variable to 0, and then also setting a variable to be an addition operation. So both of these are O of 1, right? Because, or rather, it's by assumption that they're O of 1. So we're assuming that our computer can do those operations in O of 1 time, because those are basic instructions, atomic instructions. So now there's actually three loops here. There's this one, there's this one, and there's this one. Okay, so now the outside loop. So loop one, we have a bound. So I is in between 1 and n. Okay, so I is in between 1 and n. Okay, and then for loop 2, same thing. 1 is in between, or sorry, j is in between 1 and n. Okay, so that means that all the following instructions are executed exactly n squared times, because there's like the number of times that loop 2 runs is n times, and the number of times below loop 2 is n times. So n times n is n squared. So n squared. I should write it actually explicitly right here. So these instructions run n squared times. Okay. Oh yeah, we can do while loops too. But for while loops, basically, what you want to do is you want to kind of see what kind of condition the while loop has. And why is the sigma notation used in the prof's notes? Oh, well, the prof. Okay, so basically, this is probably what the prof is doing. So he's labeling the instruction. Okay, so C5 and C7 are the instructions, right? So C5 gets executed how many times? Well, it gets executed exactly for every between 1 and n, and then also for every, I should write this as j, and then also for every j is between 1 and 1 and. So this is the amount of times that C5 gets executed, which is exactly equal to n squared times C5, right? Okay, so that kind of like mathematically describes exactly what's going on here. Now for the for these kind of set, right? And for C7 in particular. Now, Q is going from 1 to n. So that's exactly n times, right? Okay, so C7 is going, it's basically saying, okay, so let I run, let J run, and then also let Q run from 1 to n of C7, which is exactly equal to n cubed times C7, right? Because there's like, you can take out a constant. You can take out the constant here, you can move it to the front, and then you know that this is just like all these loops are separate, they're completely disjoint, their bounds do not overlap. So that means that you could just multiply the total amount each time runs. So it's n times n times n, which is n cubed. And so you know that the amount of operations that this program takes in is exactly equal to n cubed C7 plus n squared C5. Well, we know exactly what complexity this is because this is exactly what big theta of n cubed is. So that is the time complexity for this algorithm, and that is exactly what this is. Yeah. Now, for more complicated, I'm a bit confused with C5 and C7. Sorry, C5 represents the time to execute line 5. Time to execute line 5. And then C7 represents the same thing. It's simply just the time to execute. Right? Because it takes a certain amount of time to put something in a register
Mm.
and to like.
I might
Yeah.
just that might confuse them doing
Really?
it. Like
Okay.
I don't know. I feel like that feels pretty confusing. Like I don't know. This is a simpler example as well.
Okay, I should probably then
I don't
bring
think
it to
like from what I remember on the midterm, like it was just like rapid fire questions. Like it wasn't like honestly a lot of it wasn't much proving. Like yeah, you had to prove, but like for a question like this,
yeah.
like there's just 3 for loops that do constant things.
Yeah.
I don't know, just because it might really confuse them.
No, you're
Um,
true. You're so right. Yeah. Okay. So I guess like for a way shorter explanation, I would just say there's 3 loops. They're disjoint from each other. That means that their bounds don't overlap. So and they all run n times. So it's just O of n cubed for the algorithm as a time complexity, and then that would be the explanation right there. Would that be better?
yeah, yeah. I
Yeah.
think that's slightly better because there are better examples to show. Like specifically, the one that was sent
Oh, okay.
was like a insertion sort. Yeah, they were showing like because then it's slightly different. The loops aren't
Condition.
just
Yeah.
or loops, and it depends on yeah. Um,
They don't
like
have an
there's
example
a
in the review.
yeah, there's a 3A in the review. Here, I'll put it
Oh,
in the
3A. I
chat.
see.
Yeah, it's just separated between 2 different pages. Is
Oh,
annoying, but
thanks. I'm still confused how to tell for loops in cases when it's not n. Oh, okay. Okay, so this is a case where it's not n, right? Okay, so we could do this case. If I can extend or more space. Oh, I have a lot of space actually over there. Let's go use that. Okay. Okay, so now while loops, this is a more complicated. Okay, so what's the complexity of this algorithm? Okay, so we have an n-dimensional input, right? Okay, so for the first loop, j is in between. I'm just gonna write this down just like to make it clear. Like I don't know if you would write this on the exam, but j is in between n and 2. Now, while aj is more than ai, do increase I by 1. Okay. Okay. Now for every from k to 0 to j minus I minus 1, basically just set it to that and then end for loop and then just okay. Okay, interesting. Okay, so now when you're doing the time complexity, you want to kind of see what is the best and worst case that this condition executes in. Okay, so there's one case where keeps on increasing. So there's one case where AJ, right, is more than everything. Like it's the maximum. So is the max. Is the maximum, right? And what this means is that the loop basically will get executed n times. So it'll get executed n times. Oh, actually, it'll get executed up to AJ. So it'll get executed up to AJ. So in reality, it'll get executed j times, right? Because j starts at 2, and I always starts to be less than j. So you have to be careful of that. So this is this is always true. So if aj is the maximum, then this will execute maximum j times. Now note that j is in between 2 and n. So worst case, this loop will execute n times. If aj is, or if the maximum element is at the end, so this loop will execute n times. Okay. But in general, it'll execute at most j times. Now, the best case is if you terminate immediately. That's if the first element is always more than. So so this is the worst case. I should say worst case right here. Worst case j times. I'll get rid of this so it's not as confusing right here. Yeah, okay, so now best case is 1 time, right? Best case 1 time. Okay, now for the second for loop, it's from k equals 0 to j minus I minus 1. Okay, so now the second loop is from 0, so k is in between 0 and j minus I minus 1. Oops. Okay, and you know that this is worst is going to be when j and I are most separated. So at worst, this is j minus, and then when I is the least, so j minus 2, right? Because in this case, in the worst case, I is 1. And that's what I mean by worst case is worst case for this loop. In the worst case, this is 1, and then essentially it ends the for loop, and then it just does a single instruction. Okay, so there's nothing much else there. Okay, so now to find the complexity for this, you want to see it's hard unless you write it down like mathematically what it would be, which is that like this will end up computing what, like so j will be between 2 and n. And this will end up computing up to j times. And then that's the first loop, and then the second loop, you'll end up being up to, honestly, up to j minus I times, which at the worst case is up to j minus 2, right? So all in all, this is the same thing as saying, and then if I write, like, let's say, I know that you guys don't want like maybe a constant c for just a constant instruction. So basically, this would be the same thing as saying, oh, okay, j is in between n and I is always more than, or always less than or equal to j, c, and you can show that this is less than or equal to n times n plus 1 over 2 times c, which is O of, I think, big O of n squared, right? Or not big O, but like, because this is worst case, O of n squared. And to see that it's n times n plus 1 over 2, note that this summation basically turns into basically turns into, actually, no, this is right. So basically this turns into C times 1 plus 2 plus all the way up to like n, because that's what j is, and then that ends up being exactly this. Yeah, but for this one, it's pretty tricky to understand because there is everything is going on here, but to sort of like bound the runtime, you kind of want to consider worst cases, and the worst case here is that I goes up to j. So I goes up to j. So the worst case is I is equal to j in this first loop, and the worst case here is that I equals 1 in this second loop, but both actions only contribute maximum j times, right? So therefore, you can kind of bound it, something that only runs, that only goes up to j, and then you know that that's the same thing as like O of n squared. Does that sort of make sense? Okay. Okay, Jeremy, what's another way to describe this? Because the idea that I'm trying to convey is that j goes from 2 to n, and I is at most j, and so this while loop executes at most n times, and this for loop executes at most n times, or at most j
Yeah.
times. Sorry. Yeah.
So
Yeah.
they're technically bounded by n, right?
Yeah.
Yeah.
Yeah. I should actually.
So
Yeah. I should say that. Yeah.
um, right. So
So okay, you
and
can kind
also
of.
yeah,
Yeah.
I was just gonna say
No,
it's
no, go ahead.
important to see that the while loop and the for loop are like separate, like they're not inside, like they're not nested. So it so that for loop's bounded by n, right? So I guess that would be O of n, right? Um,
This for loop.
right. Like that's what it. Or
This would be
am I
O
reading that wrong?
of j. O of j. But like, yeah,
Yeah.
O of n, like maximum.
Yeah,
Yeah.
like
N squared O of n.
after when you because J okay, well J first of all, like I mean that's important to note. Like that first outside for loop, like J equals 2 to n, you could write J equals like 10,000 n and it's still O of n, right?
Yeah.
It doesn't matter because you're still going to n from a constant. It like n could be incredibly large, so it's still like looping. You know, if you go to if you take the limit, it's n. If you go to infinity. So um yeah, that you always know goes to n. It's just yeah, a matter of what's on the inside. And someone just asked, how does it change if it's nested? Well, because if you have to, like, let's say, like theoretically, I honestly didn't look at this too closely. If the while loop's bounded by n and the for loop was also bounded by n, then you just get 2n, right? If you add them together, which is still just bounded by n.
Yep.
So that's why it matters. But if they're like nested inside, then you have n times n, which is n squared instead. Um, so yeah, right, so I assume that while loop, it only increments I up to
To
how
j.
many
Yeah.
times? Yeah, up to j, which is bounded by n. So it's basically O of n, that while loop, because if it's bounded by j and j is bounded by n, then like um I guess
No,
how do
you're
you
right.
say
Yep.
that? Yeah. Because j like I actually don't know how to explain that because
I tried doing a double summation here, which is
mm,
like really like what is going on, and then like technically it's n times n plus 1 over 2, and technically that's O of n squared. I guess one way of saying it is that the maximum number of times this while loop could execute is n times.
Yeah, exactly. If it can execute up to n times, and j executes roughly n times, technically it's n minus 1, but it doesn't really matter, then you get, already you get an n squared thing, ignoring that for loop. So what do you do after finding the max number of times it could execute? Then you just, right, I would do the inner for, well, actually, I guess it depends. Like in this case, because you had to know what j does, it's hard to get that for loops or the while loops bound, I guess, or how many times it runs. So in this case, you kind of do have to start on the outside. So yeah, like I said, the first for loop goes to n. Right, that one's easy, and like I said, explained before, it doesn't matter. The 2's a constant. It could be a million to n. It's still of n because of that. Because you could have n. You don't know how big n is. And then you go on the inside. You have some constant operations like setting I to 1, but that while loop is bounded by j. But because j can be n, right? Automatically, once j is n, it's gonna do that n times ish, so it's already bounded by n. And then you have another constant operation at m equals aj, and that for loop as well is bounded by j minus I minus 1. But because j is bounded by n, right, it goes from 2 to n, and you just subtract I, which, right, it starts at 1.
Yep.
But you can basically approximate it to n. Like it's bounded by n. You not approximate 10, but it's bounded by n. You don't really know exactly. You don't need to know exactly what it does. Yeah, I don't know if that's making sense. But because both the while loop and the for loop are n, right? You add 1, right? 1 for the constant operations plus n. So that whole inner loop, or inside the for j equals 2 loop, you get a bound of n. And because the for loop itself is run roughly n times, then you multiply them together and you get a bound of n squared. If that makes sense. They can be pretty tricky though. Like in this case, like I saw the professor's example, it is true in some cases you could get averages. Yeah, I'm not really certain what would happen in this case. I mean, you could think about it. Like, let's say it's, I'll do what the professor did. If it's in order, right, A1, A2, AN, then AJ, right, it starts at 1, or sorry, J starts at 2, and I starts at 1. Because it's ordered, it immediately, it's gonna go through all of them, right? Once A goes to N, every time it's gonna be larger than AI because it's ordered. So already there you have N. But then the other loop would do the opposite because I would go basically all the way up. It would subtract from J. But it doesn't matter. They're both N. If that makes sense. I kind of rambled on a little too long there, I think. I don't know. You could also look at the reverse order case too, like descending order instead.
Yeah. So in the sorted case, the while loop takes the most, so the while loop takes it n times, or to be more precise, j times, but maximum n times for the while loop. But the for loop will execute only once. So when I talk about the for loop, I mean the for loop on line 8 executes once. Okay, but in the case where it's decreasing, then the opposite actually happens because this while loop will terminate early. Kind of have a hard time when it's not n or something logarithmic or exponential. Oh, like what's an example of that? Like binary search, probably, right? Like that kind of thing. Oh, binary search. Yeah. I'm assuming we don't have any examples of binary search, so I guess I will probably have to make up my own. Okay, so if you kind of think about binary search, right? What is the algorithm? Well, okay, it takes an L and it takes an ln value, right? And basically, it's there's like a while loop. It's like O while L of I does not equal V, then it has like an L, a left and a right pointer, right? So they're both 0 and n minus 1 respectively, where n is the size of the list. Then this while loop will execute like I think there's like if statements based on if it's less than, if it's like less than V, if it's more than V, and in this case,
I
then
could just
L will
copy
get shifted.
paste.
Yeah, actually, yeah, that'd be great.
Save time.
Okay, nice. Yeah, this is much better than me just doing it. Okay, let me copy and paste that. Oh my God. Okay, there we go. Okay, so yeah, okay, so this looks a lot better. Okay, so yeah, okay, so look at what is happening. So you kind of want to imagine what's kind of happening right here. So min, we know, is you know that min starts at 0, right? So min is at first set to 0, and max is at first set to, what is it, like the size of the list, so n. Okay, so the while loop condition is while min is less than or equal to max, and it basically takes midpoint. Now the midpoint is always calculated to be the average of the min. I'll just call it this A and this B, just because it might be easier. So the midpoint is always A plus B over 2, right? Okay, so and then it basically shifts it so that the left and right is equal to the middle whenever it doesn't line up with the key. Okay, so you kind of have to imagine the maximum number of times that A plus B over 2 is less than or equal to B, and then you also need this to be more than equal to. So you need this to be to still hold. Otherwise, it will not hold. For example, for the case, so if like let's say R low was 7 and B was 8, then their average would be like 7.5. So if you move one to the other, then it's going to end up not, this condition is going to end up getting violated at some point. I think this should be actually strictly less than. Yeah, I think this should be strictly less than. So, I mean, if we ignore that, like otherwise this algorithm doesn't work, I think, right? Because if you have a list of the same thing, then this will always be true. Yeah, okay, so basically, what's happening here is you can rewrite this condition as the same thing as saying, actually, it might be better to visualize like what's actually happening in the list. So if we look at what's happening in the list, so we have L, which looks like and then I have A0. Oh, I should actually use something else. Okay, I'll just say 0. So C0, C1, C2, and then we have up to like some number Cn. Now the left-hand side, I'm sure you guys already know how binary search works. Like the left-hand side keeps track of this side, and keeps track of like the left wall that we're looking at, and the right-hand side keeps track of the right wall that we're looking at. So at first, we're looking at n times, right? Then this kind of distance shrinks in half, right? So you can kind of see over here, over the entire execution of the loop, the distance is at first calculated to be b minus a, which we know is n, right? But at every point of execution, d is always halved. So d always gets halved by 1/2, and then it gets a quarter, and then it like at each iteration of this while loop, it always gets halved. Now it can only get halved a maximum. Okay, so you know that d is an integer, so d is an integer, because it's a difference between two integers, and you know that d can only get halved as much as it gets halved before it becomes less than 1. So therefore, you need to know that, so that means that if d is in between 2 powers of 2, so like let's say it's in between 2 to the power of k and 2 to the k plus 1, then it can only get halved a maximum of k times, right? Now, know that d is n, right, in the beginning. So that means that we want to find the number times. So we want to find the number k such that 2 to the k sits in between n and, or sorry, n sits between 2 to the k and 2 to the k plus 1, right? Should be erased right here. Yeah. And that exactly occurs when n is, or sorry, when log of n is exactly between, or log base 2 of n is in between k and k plus 1. So really, we're going to be executing this loop k times, which is exactly, which is bounded by log base 2 of n. So therefore, this whole loop gets executed maximum of like log base 2 of n. So that's sort of why this algorithm has complexity log base 2 of n. So it really comes down to the fact that the distance between the left and right pointer, which we're calling min and max here, it starts off at n, but it keeps getting halved at each iteration of the loop. And so that means that it can only really get halved a certain amount of times before the loop terminates. And the loop termination happens when d ends up becoming either negative or 0. And if we write d as being in between consecutive powers of 2, then we could see that d really can, or d, or in this case n, because it starts off at n, can really only be halved a maximum of k times. So if we were to just find the constant k, or at least a bound on it, then we can find exactly a bound on this algorithm. And because we know that if we take the log base 2 of both sides, then we can get the exponent k, then that means that this whole algorithm runs a maximum of log base 2 of n times. So yeah, does anyone have any questions about that, or there? Okay. Yeah. Okay. So, does anyone have any more questions before we kind of conclude this session? Because I think we're running now over time, right? So if anyone has any special questions, I could probably take a few now. Oh, okay, I see. Yes, yes, yes. Oh, no problem. Okay, so which one was it? What was the exact question? Okay, gotcha. And it says, Okay. Oh, proving 1-to-1 and stuff like that. Okay, so J and K, right? I'm assuming, or H probably too. These all seem like 1-to-1, like onto questions, bijective, surjective. H. Okay, H. Yep, H and L. Okay, so let's see. Okay, so H. Now to do H really quickly. What we got here is okay. Zoom in enhance. Okay, so we're given a function, right? And this function is given by some polynomial expression. So we're asked if it's injective onto both codomain are n. Okay, so now f is a function from integers to integers. So injective just means that sorry, elements map to distinct elements. Sorry, distinct elements map to distinct elements. So what that means is f of x is only equal to f of y. Oh, my thing is lagging so hard right now. How though? It's paint. Okay. Probably get a new one. Yeah, so that only means that f of x equals f of y exactly when x is equal to y. If I can write that down. If I can write that down. Okay, so f of x equals f of y only if x equals y. Okay, so you can see here that that is clearly not the case here. And the reason why it's not the case here is because like we're dealing with a quadratic expression. So if you set n to be equal to plus or minus 1, right, then f will give you the same result, right? F of n will give you that it's equal to 2. And so that means that it's not injective, right? Okay, so that kind of shows injective is not false. Is it onto? So onto, also known as surjective, just means that function goes to all the integers. Is it surjective? Well, that means that f of n must be equal to any integer m that we can come up with. Is this true? Well, no, because we know that 3n squared minus 1 is always more than or equal to -1, right? Because, and that's because n squared is always more than or equal to 0, right? So therefore, you can't even cover -2 here, and we know that we have to cover -2 in order to be considered surjective or onto. So therefore, it's not onto. So onto is not true as well. Okay, so if it's both, what if both the domain and codomain are n? Now, both the domain and codomain are n, so that means that integers that are strictly non-negative. So for the case of if f was instead from the integer, or sorry, not from the integers, from the naturals to the naturals, right? Then if you could see here, our example here where we constructed where n is a negative and a positive number no longer works here because all the numbers are strictly non-negative. And you can actually see that if f of n equals f of m, oh, okay, f of m, then that means that 3n squared minus 1 equals 3m squared minus 1. So then that means that n squared has to equal m squared. And because we're dealing with only non-negative things, then that exactly implies that n is equal to m. So the statement ends up being true if so it is injective if we're dealing with only natural numbers here. Now to prove, now to see onto. So is it still onto? Well, it's still not onto, even though 3n squared minus 1 is always, even though this does appropriately cover the range. The reason is that if we were to choose n equals 0, then, or sorry, I guess n equals 0 is not in the natural numbers, even though some people would argue that it is, but for this class, I guess it's not considered. So that means that f of 1 is simply just 3 minus 1, so it's 2. But if n is greater than 1, then that means that f of n is greater than, f of n has to be greater than 2, right? Because this expression here is exactly equal to 3 plus 1. Sorry, it's right, because it's equal to 3n squared minus 1. And you know that n is always more than or equal to 2. So therefore, you know that this whole thing is more than or equal to whatever this thing is 2. So 2 times 4, which is, or sorry, 4 times 3, which is 12, 11. So you know that this is for the case where n is more than or equal to 2. So therefore, you know that f of n is always strictly greater than 2. Therefore, there does not exist an n such that f of n equals 1. So there does not exist an n such that f of n equals 1. Therefore, that implies that it's not onto. So it's not onto. Yeah, it's not onto. So these statements just end up just being like a simple like check the definitions, end up doing some work. So injective, just to recap, just means that distinct elements always map to distinct things, and to prove it, you just simply you show that if f of x equals f of y, then that means that x must be equal to y. And to prove ontoness, or surjectiveness just means that the function maps to every possible output that it can, and that definition naturally changes as the codomain of the set changes. So for the integers, this case was not satisfied because f doesn't map to all the negative integers. And for the natural numbers, it also doesn't satisfy because it doesn't map to 1. But if you can show that it always maps to everything in the codomain, then you can then that shows that it's surjective. Okay, so that was H. I'm assuming, is there any questions there or no? Okay, does anyone, okay, so we could probably do one more injectiveness example, or like injective, surjective example. There's J here, but J. Okay, so J here, which is suppose that G is a map from A to B, and that's okay, so yeah, okay, so suppose that G is a map from A to B, F is a map from B to C, F composed with G and G are both injective. Give an example that shows F is not injective. Okay, so the thing is that F could be some function which is not injective, but it's injective on a part of the real line. And G is a function that only maps to things that F would become injective to. Okay, so if we were to consider the function f of x equals x squared, so it's a classic example of, or I mean, you can consider this. Actually, a slightly easier example would be if you looked at the function, which was like, let's say, is 0 for x less than or equal to 0. Is 0 for, we did less than or equal to 0, then let's say A is just a set, which is let's say consists of 1, 2, and 3. it's always good to just use finite sets instead, just because infinite sets you might get like bogged down by the details. And then let's say B is like a set that consists of like -1, -2, and -3. And then let's say C is like, I don't know, like 10, 11, and 12. Okay. And actually, let's say that B also consists of one more thing, which is that it consists of the special element 0. Okay, so now we could say that we could make up rules for how we want this to go, but we could say that for F, if my thing clicked to bleed. Okay, so for F, we could say that -1 maps to 10, and 0 maps to 10, and -2 maps to 11, and -3 maps to 12, right? And then for G, we could say that since it's from, where is it, A to B, we could say that 1 just maps to -1, and 2 maps to -2, and 3 maps to -3, right? Then that means that you could show that F posed with G is invertible, right? Because this is simply just the map that sends 1 to 10, and then 2 to 11, and 3 to 12. But F is not injective, right? Because we have two elements going to the same thing. And the key idea here is that F could have some mysterious elements that G never touches, such that make F not injective for its whole domain, but when composed with G, it becomes injective. So yeah, that's an example of that happening. Yeah, I think we covered those questions now. What do you think, Pablos?
I think the only thing else you need to know is what a bijection is and how that relates to invertibility. I think that might be important too.
Yeah. Is there a question with bijection? Oh, yeah, bijection. Okay, there is one question. We could showcase this. So bijection. This one right here. Okay, so bijectivity just means that it's both injective and surjective, or it's both injective and onto. So unique elements map to unique things. So if I could just write it down, bijection just means that it's injective and it's onto. So that just means that unique things map to unique things, and everything gets at least one element that it can that gets mapped to, or that maps to it. So what that means is that if you have a set, okay, so if we have A, or if we have F, then we have a set, like let's say A, and this is the classic picture right here. So you have dots here, and you have a B, and you have another set. So it just means that everything here basically has a counterpart, has its own counterpart, and nothing here gets untouched. So there's always something that maps to it. Now, how that relates to invertibility is that it actually is exactly equal to invertibility. So invertibility is the same thing as bijectiveness when we're talking about invertibility on the codomain, and that's easy to see because you see that if it's injective, then that means that you always have at least, or if it's onto, right, then there's always at least one element that you can point to. And if it's injective, then that means that element has to be unique. So that means that you can assign a unique element to every output. And so that means that you can kind of flip these arrows around so that it goes from set B to A. So that's kind of what the inverse is. So the inverse would be from this And so that's kind of what invertibility would be. Now, to determine whether something's a bijection, you can either show that it has it in inverse. So you can either provide an inverse, which is which in this case would be the same thing as x minus 7 to the fifth root of that. So that's the inverse for this function right here. Or you can show that it's injective and surjective. And to show injectivity, you just show that if f of x equals y, then that means that x to the 5 in this case would be equal to y to the 5. So that would mean that x equals y. And to show, and then that would be one thing that you'd have to show. Then you'd also have to show surjectivity. And then surjectivity just follows as well, because you can kind of choose an element that looks like this. So really, improving surjectivity, you can actually just prove invertibility right off the bat. But yeah, that's how you do this kind of question. Does that kind of describe what we're trying to show?
Yeah, that was really good. Another point I would make is, like, you might have seen, like, this in high school. I don't know, like in high school when you took functions. If you remember the horizontal line test, that's exactly what you're doing when you're proving bijectivity. You're showing that the horizontal line test passes. So if you draw a horizontal line on the function, it'll only intersect at one point. So that's exactly what you're showing with that. So yeah, that's just graphically what the bijection looks like. So if you have like a quadratic, like x squared, that one would have 2 intersections, and that one's not invertible. So yeah, that's exactly what you're doing when you're showing bijection. So yeah, yeah, that pretty much wraps up things. Is there any last minute questions before we stop the recording? Alright, I'll take that as a no. Yeah, good luck on your test next week. And
yeah, good luck, guys.
Yeah, thanks for joining and asking questions. That's really good. So yeah, good luck.